technology, who's going to speak to us about a scheme for modeling and analyzing the dynamics of logical circuits. Yeah, go ahead. So the bottom button is to go forwards, the top button is to go backwards.
Okay. Hi, I'm Amin. I'm a PhD student at NJIT, and my advisor is Professor Baltimore. So for the past few years, we've been looking at these logical circuits, and we've been thinking about modeling them as discrete dynamical systems. So since the topic is so specific, since the application is so specific, I'll go over the background and the modeling and not really go into too much of the theoretical details. So why would we even do such a thing? Well, in any sort of modeling, we would like to preserve the qualitative features, and we've shown that this is possible with this sort of modeling. And in some cases, it's easier to model these circuits as discrete dynamical systems rather than continuous dynamical systems. And in many cases, it's easier to analyze maps than flows, so that's why we try to look at Poincare maps of flows. And it's certainly easier to simulate these circuits using difference equations rather than differential equations, because with differential equations we would have to either do Runge-Kutta or some sort of finite difference scheme. But with these difference equations, we just put it into MATLAB, we iterate the difference equations, and that way we simulate these circuits. So the difference equations are just going to be voltages, and we just iterate that. So some of the terminology. What is a logical circuit or a logic circuit? It's a circuit that's made out of logic gates. And we'll talk about what logic gates are in the next slide. And feedback is really what drives the interesting behavior in some of the circuits that we look at. So a feedback is when the output feeds back into the input. So the output signal will become one of the input signals. So logic gates are just devices that carry out logical operations. So they can be electronic or fluidic or mechanical, but for the circuits that we look at, they are going to be electronic. So most of the literature are on electronic circuits. So that's why we look at, we think about these as electronic gates. So we can think about the NOR gate, and we're going to use a NOR gate in a lot of our circuits. So we can think about the NOR gate, and with the NOR gate, if we have low voltage inputs, we're going to get a high voltage output. And if we have any other sort of combination, we're going to get low voltage output. So this is like a true and false truth table.
So sorry to interrupt. So 0 true and 1 false, or the other way around? How does this work?
It doesn't really matter. So if we're using a standard system, then 0 would be false, 1 would be true, but we could use a different sort of arrangement, I guess. So yeah, it doesn't matter too much, but in our case, 0 will be low voltage and 1 will be high voltage. So a circuit that's made out of these NOR gates is the RS flip-flop circuit. And it's one of the most popular flip-flops. It was the first one designed. It's been used in primitive adders. It has been used to store a bit of memory as well. So what the RS flip-flop does is it'll either set a bit, so it's going to store that bit in memory, or it's going to reset a bit, so it's going to store the other bit in memory. So here, if S equals 1 and R equals 0, then Q is going to equal 1 and Q prime will equal 0. So in standard operations, Q prime will always be the complement of Q. And that's called setting a bit. And if R is 1 and S is 0, then Q is going to be 0 and Q prime will be 1. So that's resetting a bit. If R and S are both 0, then Q and Q prime will remain the same. So if it was 1, 0, it'll remain 1, 0. If it was 0, 1, it'll remain 0, 1. Now, the state that's avoided in most applications is the 1, 1 state. So when it first was designed, electrical engineers would avoid this 1, 1 state. One reason this is avoided is because now Q and Q prime won't be the complements of each other. So if it's 1, 1 and we follow the logic, we'll get 0, 0. So we have a problem there, but another issue is when it's 1, 1 and it flips to 0, 0. So let's say our inputs are 1, 1 and we change it to 0, 0, then we don't know what happens. We can't predict what happens just by pure logic. It depends on the physics of the devices. So that's why this is a really interesting circuit to look at, because it's simple, yet it has some of these interesting characteristics. So some of these circuits in recent years have been made with chaotic circuits. So they make chaotic gates and chaotic flip-flops that exhibit even more interesting behavior. So a chaotic circuit that's really popular is Chao Circuit. This was designed by Leon Chua in 1983, and it has two capacitors and an inductor in parallel. It has a regular resistor, and it has a nonlinear resistor. So what's a nonlinear resistor? So a nonlinear resistor is a resistor where the current as a function of voltage is nonlinear. So we remember from freshman physics courses that V equals IR in a standard resistor. But, so we can think of the current there as a function of the voltage. So I is going to be V over R. So we can think of the current as a function of voltage. But in a nonlinear resistor, that relationship isn't linear anymore. So when Chao built his circuit with this nonlinear resistor, he had something that was a resistor that acted as a piecewise linear function. So the current is a piecewise linear function of voltage. So that's a way we can think of a nonlinear resistor.
Sorry, shouldn't that be a step function where you have 0 and 1 to be more accurate instead of piecewise? Because that's a standard model, if I'm not mistaken, of how the current operates discretely.
Okay, for nonlinear resistors?
Yes. Mm-hmm.
Okay, yeah, I think that could be a case. I think there are different ways that they make nonlinear resistors as well, though. So, I'm not sure exactly which one he looked at,
Okay.
what it looks like. But, yeah, I guess it could be a step function, yeah. And what he did was he took measurements of the capacitors and the inductors. So he looked at the voltages through the capacitors and the current through the inductors. And he measured it in an oscilloscope, and he sees that we get some sort of thing that looks like a strange attractor. So we get a strange attractor looking thing. So that's pretty interesting in itself. And a year later, Matsumoto came up with a model, a continuous dynamical model for this system that replicated the behavior quite well. So here he uses 3 ODEs. The first two are the voltages for the capacitors, and the last one is the current for the inductor. And here C1 and C2 are just the capacitance, L is the inductance, G is the conductance of the resistor, of the regular resistor. V's are the voltages, so these should all be uppercase V's, like that one. So that's a typo. And this is the effect that the nonlinear resistor has on the voltage. So in the literature, they call this attractor a double scroll attractor. So from Chao's circuit, in recent years, people have made other sort of circuits. So one thing that has been made is a NOR gate implementation out of Chao's circuit. And this has been done by Sinha, Murali, and Ditto in 2003. And the schematic itself is pretty complicated, but basically what happens is, and I was hoping to make this bigger, but it wasn't really quite fitting in. they take Chao Circuit and they use a threshold control unit, and that way they get the desired outputs for a NOR gate. But we see here, so these are the two input voltages, and this is the threshold voltage. So we see that whenever it's 1-1, we get these wild oscillations, and it seems kind of random. So this is a property of the construction, it seems. So this is just for the NOR gate. Now, with the NOR gate as inspiration, Cafagna and Grassi in 2006 developed this RS flip-flop. They designed this RS flip-flop similar to the NOR gate implementation. And they see the same sort of thing. So these are the two NOR gates, and these are the two inputs. So this input and this input are the same, and these two inputs correspond with each other as well. Not sure why they flipped it around, but we see here that for both of the NOR gates, whenever it's 1-1, we also get these wild oscillations. So this is really the sort of behavior that we wanted to capture in our models. So in 2009, when I was an undergrad, we looked at these things and modeled it in an ad hoc manner. And we came up with this model, and we saw that it does replicate the behavior seen in the physical realizations of these circuits. And from the model, we get Hopf bifurcations and cascading Hopf doubling bifurcations, and chaos is shown by identifying horseshoe-like behavior. So my professor did prove all this, but we won't go through the proofs today. So we weren't really satisfied with this because it was done in an ad hoc manner. What we wanted to do was we wanted to go from the ground up. So we wanted to go to the level of the gates and try to get models for the gates, and then build models of any sort of circuit using these models for the gates. So we came up with some models, some simple models for the gates, and we used these to model the RS flip-flop. So here, the models for the gates here are basically the macro effects that the gates have on the incoming signal. But there are some micro effects, so we leave those micro effects as functions of the incoming signal, so we can tweak these functions to replicate the behavior that we need. So we use this in the RS flip-flop construction, so we get this sort of model from there. So we can tweak these functions. So back here, we can either have it, as phi of x equals x and psi of y equals y, or we can have something that's nonlinear. So here we used a little perturbation. So we used basically phi of x and psi of y equals x and y, but we perturb it just a little bit. And this is going to give us chaos on the line y equals x. So it gives us some interesting behavior. So here's a movie for it. So it's kind of bouncing around, the iterates are kind of bouncing around. It's going to look seemingly random. There's going to be some sparse areas and some dense areas, and it reminds us of kind of like the Cantor set.
Just going to view full screen.
Full screen.
Yeah.
But we weren't satisfied with this because when we look at the literature and we look at the physical realizations of these circuits, we see that if we have some sort of Poincare map, we're going to get some two-dimensional chaos. It's not going to be just on a line. We need chaos kind of all over. So we did develop a model for that, where the functions are quite complicated in this case. So the functions can get very, very complicated. But basically what these functions do is we consider small perturbations and then a jump and then oscillations. So that's what these functions are. So we're going to have oscillations, a jump, and then oscillations instead of just a straight line. So from there, we're going to get chaos in 2D. So it's going to look a lot more random, and it's jumping from different regions to other regions. So it's going to be kind of jumping like this. We see that a line is filling in, but it's not really filling in on that line. It's actually jumping to another region and then coming back.
Well, if I'm not mistaken, the line also moved in this video where it did not move in the previous video. Or is that...
That might just be because of the resolution,
I see.
or the dimensions of the plots in MATLAB. And we can really see that over here. So I guess I should do view full screen. So yeah, we can really see that over here where it tracks the previous iterates as well. And we can see that it's bouncing around from region to region. So one day I kind of designed this, this ring oscillator using 3 NOR gates. So it's like a 3D RS flip-flop. It's really not used in applications. It's just something that some toy design that I came up with, and we wanted to see what would happen if we modeled this and see what happens to the iterates. So we did this, and we get something quite interesting. So we're going to get chaos in 3D now, and it's going to look a lot more random. We get some really nice behavior, really nice structures, and if anyone was at the last sectional meeting, the difference equations session, there my advisor's former PhD student talked about trellises, and my advisor was saying that we might have the same sort of thing going on here. We might have these trellises. So we're going to do some analysis on that. So that was just kind of a toy thing that we came up with. So in the future, we're going to do some more analysis on the existing models. So for that 2D case, we're in the process of proving that it is chaotic. We did prove it for the 1D case. And we would like to get better models for the individual gates. So for the gates, in the micro scale, we left it as functions so we can kind of later on pin down what those functions should be from physics. So we want to look at the physics of these gates very carefully and try to pin down what those functions really should be, instead of just coming up with functions in an ad hoc manner to replicate the behavior. And we would also like to, and we are actually coming up with a new algorithm to come up with more robust models. So here we wanted to focus on that 1-1 case, and we wanted to really see what happens there and capture that behavior. But we would also like to capture any sort of behavior. So we are coming up with more robust models as well, and we would also like to do experiments on some of these toy circuits that we come up with. And thank you.
I'd like to ask a question. How come you only have AND or? Why do you not have conditional gates, if then?
Oh, do you mean like a XOR or an XOR? Or?
Yes.
Okay, so in flip-flops, those aren't really used. So they might be used, but they'll be used in combination to make another gate. So if we look at, let's say, the JK flip-flop or the T flip-flop, those those XOR or XOR gates aren't really used. They're not used by itself. So the reason they're used a lot is because it's faster. So those are faster gates. So sometimes they'll use that instead of, let's say, a NOR gate, but they'll use it in combination to create a NOR gate.
Okay, other questions or comments for Amir? You go ahead.
Just to note that they're beginning to build a variety of these nonlinear resistors.
Right, yeah.
Might be,
They make it in all these weird sort of ways, yeah.
that are coming out.
Yeah.
That becomes, I think, an interesting question to actually ask about, about what some of these will do in actual circuits. And the other question that's sort of more philosophical, maybe further out, is that I always thought it would be kind of neat to get one of these where you can control the amount of chaotic behavior and then actually think of building hardware that would directly apply some analogs of the simulated annealing algorithm. The D-wave quantum computer seems to do that, but people have argued that it's not really so much quantum as this random behavior. I think it'd be interesting to look at.
Also, based on the observations, if I'm not mistaken, when you make the period very short, that's what sort of creates chaotic conditions, but it seems like longer periods don't create. Am I correct on that?
I'm not too sure. So
when you had these like
the waves, right?
When you had these steps, when
Right.
they were when they became shorter and shorter, then they transitioned to chaos. Because when they were long, they were steady, but then it seems like when they were shorter, all of a sudden they stopped behaving in steps.
For the threshold
Yes.
voltage, or okay. I guess I'll have to look into that more. I'm not really sure about that.
Because there has to exist some like borderline that goes from stability. It seems like when you make the periods shorter, based on what I've seen, that's what sort of slowly transitions into chaos. When you have longer periods, then it's very steady. It goes step and step.
Okay. I'll ask my advisor about it.